Hey guys, in this video I want to prove Menger's theorem using max flow mean cut. Well, we shall focus on the vertex version of Menger's theorem, which says that if we have a graph G and x and y are two distinct vertices in the graph such that they are not adjacent to each other, then kappa of xy is equal to lambda of xy. Let me remind you what are kappa and lambda of xy. Kappa of xy is the minimum size of an xy cut, whereas lambda of xy is the maximum number of pairwise vertex disjoint, or rather internally disjoint paths from x to y. Well, we should break down the proof into two parts. So first we're going to show, by using definitions, that lambda of xy is at most kappa of xy. Then in the second part, which is the more difficult one, we are going to use max flow mean cut to show that kappa of xy is at most lambda of xy. And hence together we have proved that kappa of xy is equal to lambda of xy. Let me start with the first inequality. Here we want to prove that the maximum number of xy internally disjoint xy paths is at most the minimum size of an xy cut. Well, to do this, let us take a minimum xy cut, let's say u, of the graph G. We can visualize this as follows. The set u is a minimum xy cut. Therefore, if we delete u from the graph G, we will then disconnect the vertex x from the vertex y. Now, let us examine the paths that go from x to y. Since u will disconnect x from y, it means every path or every xy path must go through the set u. Right? For example, if you have a path like this, then it must come to some of the vertex in u before we can continue to the vertex y. If we have another path or another xy path, it must be passing through u again before it comes to the vertex y. Alright? So if we have a set of vertex disjoint paths like this, then every one of them must cut through the set u at distinct vertices. I mean passing through distinct vertices in u because they are internally disjoint. Therefore, if we have lambda of this, right, if we have lambda of these xy paths, then this number lambda must be at most the size of u. Hence, we deduce that lambda of xy is at most the size of u. But remember, u is a minimum xy cut whose size is equal to kappa of xy. And therefore, we have proved the inequality that we wanted to show from the beginning. Do you follow me? Okay, let us now move on to the second part. In the second half, we want to invoke the max flow mean cut theorem. And in order to do this, we must first construct a network N. And we're going to do this in the following three steps. All right? So, first of all, this network N will contain the vertex x as the source and the vertex y as the sink. Remember, x and y are fixed by the theorem. Okay? The first step is to replace every edge in the graph with two directed arcs. So if the edge is uv, it will be replaced by the arcs from U to V and from V to U. The following figure is an example. So here we have a graph G with X and Y identified. And we're going to set our X to be the source in the network, and then Y to be the sink in the network. In the first step, every edge in the graph will be replaced by two arcs. So for example, the edge AB is now replaced by the arc from A to B, as well as from B to A, so on and so forth. This is not the final network that we're going to use, because in the next step, we are going to further modify this. So, in step 2, every vertex which is not the source or the sink will be split into two vertices called the plus vertex and the minus vertex. So for example, if W is a vertex which is not the source or the sink, then we will split this into minus W and plus W. Okay. Furthermore, a new directed edge will be formed starting from W minus or minus W to plus W. And this additional arc that we introduce will be called an internal arc of the network. Okay, so whenever we mention about internal arcs later on, it refers to the arc starting from the minus vertex and then is directed to the plus vertex. So what happens now to all the previously existing arcs when we introduce the splitting? Well, all the other arcs will be replaced by the following. Since we have split the vertex into the plus and the minus vertex, every arc directed from U to V in the network will be replaced by the arc directed from the plus vertex to the minus vertex, as long as they are not the source or the sink. You follow me? So the basic idea is the plus vertex will be directed to the minus vertex. Okay, if the arc from U to V was present previously. If the starting vertex is the source or the sink, then it will be directed to the minus vertex. Okay, that is the second case here. If U is one of the source or the sink, and U was directed to V, this will be replaced by U directed to V minus. Remember, we do not split the source or the sink. So the U here will remain as U if it is the source or the sink. But if it was directed to another vertex V previously, and because of the splitting, there are two vertices corresponding to V, which are the minus vertex and the plus vertex. But we're going to direct that to the minus vertex. Okay, so that is the second situation. In the last case, when the vertex V is the source or the sink, then the arc will be replaced by an arc directed from the plus vertex to the vertex V. I guess it will be easier if we look at this using one example. Let's take the previous graph, for example, where after step 1, we have the following network. Well, it's a bit tedious if I do that for every vertex. Let me just focus on the arcs from X to A and from A to B for illustration. Okay. So after step 1, we have the source directed to A, another arc in the opposite direction, and we have an arc from A to B and another one in the opposite direction. Okay. According to step 2, we are going to split all the vertices which are not the source or the sink. So in this case, the vertex A will be split to the minus vertex and the plus vertex. Similarly, the vertex B will be split into the minus vertex and the plus vertex. The source will remain the same. Okay? As mentioned in step 2, there will be internal arcs directed from A minus to A plus and B minus to B plus. Let me draw the internal arcs using a red arrow. Okay, these are the new arcs introduced in step 2. Also, according to the rule, if there is an arc from A to B, then we're going to direct from the plus vertex to the minus vertex. So indeed, we have an arc from A to B. So the rule is that will be replaced by A plus to B minus. You follow me? Also, we have an arc from B to A. And these are not the source, not the sink. So it will be directed from B plus to A minus. So the rule is always from the plus vertex to the minus vertex. Okay, that is what happened here for the arc from A to B and B to A. If one of these vertices involve the source or the sink, then the rule is slightly different. So for example, we have an arc from the source X to A. So according to the rule, it's going to be from the source to the minus vertex. So here, this arc will be replaced by this arc here from the source to the minus vertex. You follow me? Okay, let me label the source. And likewise, if you have an arc from A to the source, so that is the third case over here, right? You have a vertex directed to the source. So you'll be from the plus vertex to the source. So you'll be from the plus vertex to the source. Okay, I hope now you see how we actually carry out step 2. And if we do this for all the arcs in the network, we'll get the resulting network. Okay, after step 2. All right, let us now move on to step 3. Step 3 is about assigning capacities to the arcs of the network. Precisely, every internal arc will be assigned a capacity of 1 unit, and all the other arcs will be assigned a capacity of n, which is the total number of vertices in the graph G. So for example, in the graph G that we used just now for illustration, there are 5 vertices altogether. Therefore, every arc which is not an internal arc in the network N that we constructed will have a capacity of 5. Whereas all internal arcs will be assigned a capacity of 1, as given here in the figure. Okay, we are now ready to prove the inequality that kappa of xy is at most lambda of xy by making use of the network that we have constructed above. First, here are some observations about the vertices and their arcs. Every vertex of the form W minus must have exactly one arc going out from it. And this must be the internal arc directed from W minus to W plus. The reason being, in step 2, except for the internal arc, all the other arcs are directed from the plus vertex, if you remember. So the only time when we have an arc directed from a minus vertex is when we have internal arc. Okay, so that's why we have this observation here. And likewise, for the same reason, the only time we have an arc directed into a plus vertex is when we have internal arc as well. And therefore, every vertex of the form W plus also has exactly one arc coming to it, and this is precisely when the arc is an internal arc, right, given by W minus being directed to W plus. And later on, we're going to make use of these observations in our argument. All right. We will break down the proof into two steps. So first, we're going to prove the inequality that lambda of xy is at least the max flow in the network. And then we're going to show kappa of xy is at most the mean cut of the network. Then the result follows by combining these two inequalities together. This is because max flow is equal to mean cut. All right. Let me now show the first step, where lambda of xy is at least the max flow. So let F be a maximum flow in the network. Let's say the value of the flow is little m. And here's an important observation. If there is a flow into a minus vertex, let's say u minus, then the value must be 1. Okay, this is because there's only one arc directed from u minus. If we have a flow into the vertex u minus, and because there's only one arc going out by observation 1 above, and this arc which is going out has capacity 1, it means that the flow into u minus must have value 1 as well. So the flow into u minus must be 1, and the flow out of the vertex must also be 1. And if we trace the flow, it must travel from the source to the sink. Okay, this 1 unit flow must travel from the source to the sink. Furthermore, if we have m units flowing out from the source, then all these paths that contain this 1 unit flow will not share any common vertices except for the source and the sink, right? Because we only allow 1 unit going in and 1 unit going out. If they happen to share, a common vertex, then there'll be more than 1 unit going in which case this is not possible, right? Because as given in observation 1, there could be only 1 unit coming out from this vertex u minus. So this means the m units flow into, these m unit flows from x to y translate into m internally disjoint xy paths in the underlying graph G. You follow me? And this implies that the number of these internally disjoint xy paths that we can find must be at least this value of flow that is allowed by the network. And since we have chosen m to be the max flow from the beginning, we have the inequality. Okay, maybe let me try to illustrate this using the diagram. So for example, if we have 1 unit flow from x to y, so it must come to some of the minus vertex. Let's say there's this flow into a minus, and because there's only one arc going out with capacity 1, so there must be 1 unit there going out from a minus, and this means there can only be 1 unit coming into the vertex. So if we trace the flow, it will give us a path from x to y. If we have another 1 unit going out from x, and if we trace this flow eventually to the sink y, the flow will be disjoint from the previous one. You follow me? And if we translate that back to the graph G, it will give us two internally disjoint paths. And that is why the number of internally disjoint paths must be at least the max flow in the network. And hence we have shown the first step. Let us now move on to the second step. To show that kappa of xy is at most the mean cut, I'll first show that if we take any minimum cut, let's say k, of the network. So let's say this is a minimum xy cut of the network N, then all the arcs directed from the set S to the set T are internal arcs. Here's how we can visualize it. So if we have S over here containing the source, and then the set T containing the sink, I want to show you that if you look at any arcs directed from S to T, those are internal arcs. Alright, which means all these arcs have capacity 1. Right, to prove this, okay, to prove that all these arcs are internal arcs, I'm going to assume for a contradiction that this is not the case. Well, if this is not the case, it means that there is an arc directed from S to T which are not internal arcs. Well, if there is such an arc, then the capacity will be n, which is the number of vertices. Okay, let's assume for a contradiction that not all the arcs are internal arcs going from S to T. That means we can find a non-internal arc. Directed from S to T. But remember, a non-internal arc has capacity equal to the number of vertices. So let's say this is a non-internal arc going from S to T. The capacity is given by n according to our construction. Which means when we calculate the capacity of the cut, we must take into consideration of this arc whose capacity is n. Therefore, the capacity must be at least n. I want to show you that this is not possible for a minimum xy cut. This is because we can find a cut whose capacity is strictly less than n. I call this the cut K star with the partition S star and T star, where the set S star consists of the source together with all the vertices which are the endpoints of the arcs starting from the source. And T star is just the complement of S star. Now I want to show you that this is a cut whose capacity is less than n. Well, here's how we can visualize the cut. So we have the source X, and then we have all the vertices which are the endpoints of the arcs directed from X. And all the other vertices are inside this T star, including the sink. Now inside S star, all the vertices are minus vertices, except for the source. All the arcs going out from S star are internal arcs. Okay? Therefore, the capacities of these arcs are 1, which means the capacity of the cut K star is bounded above by the number of vertices which have the form of a plus vertex. Now, if you look at the vertices inside T star, excluding x and y, there are at most n minus 1, at most n minus 2 such vertices, right? The 2 here means we're excluding the source and the sink. Therefore, the capacity of K star is at most n minus 2, which is strictly less than K. This gives us the contradiction that we are looking for, because when we started out, we have a minimum cut. And by assuming there is a non-internal arc, we deduce that the capacity of a minimum cut is at least n. But how can this possible, since we just found a cut whose capacity is strictly less than n? So this contradicts the minimality of the cut K. And therefore, all the arcs going from S to T in a minimum XY cut in the network must be internal arcs. Let us record this down in the following statement. If we have a minimum cut in the network, all the arcs directed from S to T are internal arcs. And I'm going to box this up and denote this statement by star. Finally, we are ready to prove the inequality that kappa of xy is at most the value of a minimum cut in the network. And the idea is to construct a vertex cut, or rather an xy cut in the graph G using a minimum cut in the network. So if we let K to be a minimum XY cut in the network, we want to construct a XY cut U in the graph G. All right, so we are translating an XY cut in the network to a cut U in the graph G. And this is how we are going to construct the XY cut U. So we're going to let U to be the set consisting of all the vertices U such that the minus of U, right, or U minus, is inside the set S of the minimum cut, whereas U plus is inside the set T of the minimum cut. Well, it's easy to see that the size of U is equal to the capacity of the cut. Okay, so because these are all internal arcs according to star. So if you count the number of 1 here, you are actually counting the number of vertices U that we collect inside the set U. All right, so the size of U is the capacity of the cut. And therefore, it remains just to show that this set U is an XY cut in G. Then the fact that it's a XY cut implies that the size must be at least the minimum size of XY cut, which is given by kappa of XY. And from the previous line, the size of U is the capacity, which is the minimum cut of the network. And we will prove the inequality. You follow me? So we just need to show U is an XY cut. That means we want to show that if we delete U from the graph G, then there is no path connecting X and Y. All right? To see this, let us consider a path from X to Y in the graph G. So here the path P starts at the source X, or the vertex X, and then followed by the vertex U, U1, U2, U3, and so on until ut before it reaches the vertex y. This path is translated into a directed path in our network N. Remember, the edge from x to u1 will be replaced by the arc from x to the vertex u1 minus in the network N. Also, we have internal arcs from u1 minus directed to u1 plus. And also, the edge from u1 to u2 will be replaced by the arc from u1 plus to u2 minus, so on and so forth. Okay? This will be a directed path, denoted by P with an arrow at the top, in our network N. Notice that along this path, there will be an arc which is directed from the set S to the set T. In other words, if we were to visualize this path, it will be a path starting at X, and then at some point it must cross over to the set T, okay, in order to reach the sink Y. So there will be one arc here which go from S to T. But according to our previous observation, which we denote by star, this arc must be an internal arc. Okay? So this arc here must be an internal arc. Therefore, it has the form U minus being directed to U plus. Alright? And the capacity of this arc is 1. Right? If you have another path like that, when it crosses over from S to T, it will be an internal arc that looks like this. Now, what happens if we delete all these internal paths? If we delete these arcs, then the source will be separated from the sink. Okay? That's why we write down here saying that deleting internal arcs from S to T is going to break the path. But translating back to the graph G, deleting the vertices in U from G will separate X from Y. Remember, U is constructed from the internal arcs from S to T. So if we can separate X and Y in the network by deleting the internal arcs from S to T, we can separate the vertex X from Y in the graph G. And that proves that the set U is an XY card of G. And we are done because this is exactly what we want to show when we set out in the beginning. Okay guys, I'm sorry for such a long proof. I hope all this makes sense. Okay, that's all for now. See you next time.